Yes, I know about that. It's a fighting period, so it is very exciting. Closest friends. He actually told us, like, if you see him, you will see him.
Okay.
Send him regards. So regards from him. Yes. Thank you so much.
Okay, so perhaps we can get started with this session. So I'm Gonzalo Llena from EBA Zurich. I will be chairing the next session of planning and scheduling and supply chain. So we'll have three presentations, three speakers. Just to clarify, we will do as before. So we'll have the talks without Q&A, and later on we will merge the Q&A session of this session and the next one. So we're going to finish hopefully at 3:50. We will actually go for the break and the photo. We will continue with the next session, and then all together we will have the 5 speakers here as we did before, right? So let me just say a few words about the first speaker. Is Professor Metin Turkay from Turkey. So he is now professor and head of the Department of Industrial Engineering at University in Istanbul. He studied his PhD in Carnegie Mellon University in 1996, and then actually he spent also some time in Mitsubishi Corporation in industry, and then he came back to academia. So he has been ever since working intensively in the context of applying optimization to a range of problems, mostly including supply chain management and logistics. And he has received many awards in recognition to his outstanding work, including awards from the ASDHE and also from the Curtis Science Foundation and also IBS. So the talk is entitled Reinforcement Learning for Complex Integrated Planning and Scheduling Problems, where we will see how we can apply machine learning in the context of this supply chain management problem. So thank you for coming, and with that,
Thank you, Gonzalo, for this introduction. So this looks highly sophisticated. I hope I can use it properly. Good afternoon. First of all, I would like to thank the organizers for this basically excellent event. I can imagine how basically difficult it is to basically bring all of these experts together in Hangzhou, and also basically spur interest from PhD students and also local industry. So today I'm going to talk to you about reinforcement learning. It's a hot topic, but I'm going to make it as understandable as possible by focusing on main aspects only. And the topic that we are going to talk today is planning and scheduling problems. So this happens to be a very important area. And by the way, I'm from Koç University. Koç University is in Istanbul, located at the intersection of Bosphorus that divides Europe and Asia, and also Black Sea. So our campus is located in the national forest. It means that it's a national preserve area because it has proximity to basically historical sites and natural sites. So we have several faculties, and College of Engineering happens to be one of the most important basically productive faculties. We are a very young university that was established in 1993, and College of Engineering was established in year 2000. I'm one of the first founding faculty members to establish industrial engineering department, and since 2000 I'm basically there. So let me talk to you about my presentation outline. First, I'm going to talk to you about planning and scheduling problems. I'm sure most of you know this, but I'm going to skip this very quickly just for orientation purposes. It's an NP hard problem. Actually, the previous session highlighted this importance of NP hardness. So it means that it is very, very difficult to solve these problems. Computationally, it is very difficult. If you're lucky, in some instances, you can get an answer in reasonable amount of time, but most of the problems you will not be able to get an answer to this problem. It's a very challenging problem. And there are different solution approaches. One of the approaches is experience. So manually, people basically establish a solution that works, and an expert basically recycles this solution throughout his or her lifetime of occupation, adding and subtracting some of the things. Constraint logic programming is also applied. Basically, it involves representing the problem as a logical propositional logic system of equations, and you are asking for feasibility of the solution rather than optimality. But Ignacio basically with his student worked on the approach that will basically combine constraint logic programming and mixed integer linear programming. But again, it is basically applicable to only small scale problems. Then we have the MILP, optimization models and solution algorithms. This has been the dominant basically solution approach, but it suffers from computational complexity issues. Computational complexity is there. Whatever algorithm you use, you are not going to be able to eliminate computational complexity. And planning and scheduling problems have to be solved very frequently. And one of the issues that explodes the system is the time resolution. Are you going to do time resolution of 1 second, 1 minute, 1 hour, 1 day, 1 shift, 4 hours? And also industry, basically due to managing supply chain operations before and after the production operations, want to basically increase the speed. Just last week, one company, global company, said that they want to do production planning for 12 weeks with 1 hour resolution. If you calculate 24 times 12, it means that you are going to multiply your system of equations by 12, multiplied by 24, right, with 1 hour resolution. If your system of equations are small, it will be multiplied by 288 times, right? So if you have a simple system. So planning, replanning, and schedule as changes occur is an important issue, because if you are considering several weeks, things will happen, right? Accidents will happen. Machines will break down. Orders will be cancelled, right? So there is a need for replanning and rescheduling all the time. And the problem with the current approaches is the memoryless structure. Imagine you have developed a mixed integer linear programming approach to solve this problem, and once you solve it, probably it will take several days for a realistic industrial application. And what you are going to do is you are going to forget about the solution, and you will restart solving the same problem again at every frequency, right? Once a week, once a day, etc. Every day the same. But the industry actually wants a solution every 10 seconds, 1 minute, right? So for this, after saying, I mean, don't get me wrong, I'm a very theoretical person. I did my PhD on developing generalized disjunctive of the programming algorithms for solving mixed integer nonlinear programming problems. So I will basically here combine the theory and also practical challenges how to adopt these basically theory. So we adopted reinforcement learning algorithm. So it's a actor-critic setting. I'm going to tell you about the setting. And we need 3 things. The first thing is environment, which is simulating the environment. And the second is basically the actor that basically makes a new decision, and also performance evaluation for the critic. So we need 3 independent entities for managing planning operations effectively. All right. So we told you that it's an MPI problem, and these problems basically are solved by MILP, and basically state-of-the-art software has some limitations. So commercial softwares like Grovis, Cplex, I'm going to highlight with an example, takes 2-3 days to solve one instance of the problem. 2-3 days. Then open source softwares are available, but I mean, in terms of performance, these are probably 10 to 100 times slower than these commercial software packages. And also, memoryless structure, we talked about this, and also operational decisions require, very frequent updates on this. So reinforcement learning basically is a pretty new subject, and it follows Pavlov's dog experiment. As you know, Pavlov basically trained the dog for lunchtime or dinner time by training. So it's a similar approach. What you do is, if an agent makes a good decision and realizes a good outcome, in that case you provide a report for this agent. If the decision and action was bad, resulting in bad consequences, in that case you have to basically issue a penalty. So reward and penalty works together. So this is in a way how we train our students, right? Our students perform very well in the exam, we give good grades, right? And praise them. Even in my case, what happens is I travel internationally, I say that whomever scores 100 is going to get a 10 euro basically chocolate bar from me, right? So if students perform very poorly in that case, I will say that, okay, you have to repeat this course because we are not done yet. So similarly, so this motivation, right, I mean, encourages a student to do better and also not fail, right? So this needs basically an interference and to basically address the disadvantages of MILP models and algorithms. And also, you may need very low computational time once you have the digital description of the problem or digital twin of the system. And this approach is more suitable for dynamic environments where things change very frequently, as well as edge computing platforms where you operate on complex systems with minimum available data. So challenges include training, right? We need to have enough sampling. So imagine that this is a weakness for mixed integer linear programming because you are doing planning almost every hour, every day, right? This means that if you are able to collect the data on past actions and also past outcomes, you can use this training, real data. And also, for the other case, you can use basically simulation based on digital twin to generate enough data so that you can basically issue a deep reinforcement learning algorithm to basically learn the system properties. And this approach, again, I mean, there is an issue with the activation function, which is non-convex and non-linear. This may get stuck in local optima, but there is the theoretical issue that has to be addressed separately because it is not an issue with this algorithm, reinforcement algorithm only, but it is basically an issue with neural networks and reinforcement learning at its core. Basically, you cannot guarantee global optimality because you are not after global optimal solutions, a solution that works for you. Okay. So main basic setting is you have an agent basically making a decision. For the next plan, these are the schedule, these are the decision values. And these actions will be transferred to the environment. The environment is going to simulate what will be the consequences of these actions, what will change, when the particular order will be processed and produced, in which machine, in which quantity, setup times, etc. All of these, and will issue basically a state of the system. Then we need an independent evaluation of this. Basically, this will basically transfer into T time periods. So you are going to basically make a decision at small t, and you are going to execute this until capital T, which is the end of the horizon. When the end of the horizon is reached, basically this entire system has to be evaluated with respect to this performance. So performance evaluation is done by policy, pi 0 to pi theta. So in that case, what you can do is you can basically evaluate the performance of these policies using the reinforcement learning algorithms. So input layer is going to continue all of your decisions and current state of the system, and output is going to be a performance metric that will be used for evaluating the performance of the action. So in this case, what you do is you basically generate all what-if scenarios, and out of these scenarios, courses of action, you have to select one policy out of it, right? So we have to maximize the basically rewards. At each time period, we are going to get a reward. Basically, this reward is going to say that based on your decisions, for example, in planning system, your machine capacity will be overbooked. Your inventory, basic inventory storage, intermediate storage is going to overflow, etc. These will result either penalties or some rewards. So you have to collect all of them throughout the basic current time until the horizon. End of the horizon could be 12 weeks in extreme case, or could be 24 hours, 1 day, right? So you have to find parameters that basically maximize this, total reward function. Right? So you can basically have improvement in the policy. So whenever you evaluate the functional performance of the system or your decisions, basically you can update and you can say that, okay, this basically gradient towards this policy decision is taking me a better solution. So I will illustrate this with this graph. Imagine that I am at point 0 here, and I can, in terms of time resolution, I can have millions of decisions, right? So all of these decisions will have an outcome, and the red ones are basically favorable. It will be improving. This is not a boundary value problem, right? It's a trajectory problem. So it will tell me that, okay, if you follow this trajectory, you are going to be within the feasible region first. You are not going to violate any system constraints. Second, your reward function is going to be maximized, right? So out of these, our basic search is going to find gradients such that we are not going to find infeasible solutions, or we are not going to basically come up with infeasible solutions. These are also okay for feasibility perspectives, but our objective is to select courses of action at each time period so that we maximize our reward. Okay? So for reinforcement learning algorithm, what we need to do is, in order to have a better representation of the system, we have to do a simulation environment. And in the simulation environment, we employ Monte Carlo simulation, and basically we say that what happens if I do this as a consequence, right? So, and we can collect n samples. This could be true data, samples from data, or this could be true simulation. If you are sampling all of these through data, it is faster, quicker. If you are doing this through simulation, it depends on the complexity of the simulation. If your simulation model is very complex, in that case, it's going to take a lot of time to compute. So this basically three main players or software agent. One of them is agent, makes a decision. One of them is environment, calculates the consequences of this decision in the time period that you define. And the third one is critic. Criticizes and tells you that you made a decision at a time period t+5, and due to this decision, t+8 inventory is overflew, right? Therefore, there's a penalty for you for making this decision, wrong decision in t+5, right? So all of these decisions are evaluated by critic. So evaluation of feasibility, at the core, what we do is for any planning and scheduling problem, we start with mixed integer linear programming model. We don't give away, right? So MILP representation of the problem is there, but we divide this problem into two different pieces, right? One of the pieces is for agent and critic. There we are basically looking for feasible solutions. I mean, if you have experience with mixed integer linear programming, for example, branch and bound, etc., what you will see is every second, even 1 million size problems, every second a solution will be generated. Whether this solution is a relaxed LP or an infeasible LP, it's not an issue. But with these are basically solution algorithms and current computing infrastructure. Even the largest problems you can basically evaluate in an instance within 1 second, whether this is feasible or not, right? So we are doing this for basically agent, and for critic, what we do is we separately evaluate the objective function, right? So actor says that, okay, I made these decisions, but at this point, I became infeasible. So this is pretty much in multi-objective setting. So in the case, you can basically formulate this as a profit maximization, environmental impact minimization, setup time or capacity loss, etc. All of these can be basically defined as different objectives. So I'm going to, at this theoretical, I know that it's not deep theory. I think it's understandable, 3 main players in the algorithm, but I'm going to highlight this for students' benefit, 2 important applications that we have completed within several weeks. So one of the basic examples is a global manufacturing company. It's a global company that has factories in 30 different countries, and basically they have the largest manufacturing facility in Turkey. It has 7 integrated factories, and this company is basically producing 35 million appliances, including Miele, Gaggenau, Thermador, Bosch, Siemens, and Prof. These are basically global brands. So if we basically always start with MILP, MILP has 18 million variables, 4 million of them are 0-1 variables. So it is basically, even with commercial software scale, this is not tractable, right? We have used the most recent version of Groby 11, and it was not basically reachable. It's not possible. So, moreover, this company has frequent changes. Orders change because they are producing for these 6-7 brands. Orders cancel, orders come in, orders change, etc. Machines break down because in every basic manufacturing facility, 7 of them are integrated. At least for each of them, you have 200 robots. Robots are our friends helping us, but they break down, right? Like people, right? They break down. And the machinery breaks down. So what happens when one machine breaks down? You have to replan and reschedule, right? And also quality issues, right? So 35 million appliances are produced from raw material, processing, etc. There will be frequent quality issues, right? Probably 1 or 2% of your production will be rejected out of spec. So we developed this, and what we do is we receive data from SAP systems for orders and others, etc., but also we receive a signal from manufacturing execution system every 10 seconds. So we integrate with SCADA systems and PLCs. Every 10 seconds, all of the factories send us a single signal, whether it is functioning properly, which order they processed, right? So is there a quality issue with your imaging system? Send us, basically, it says that paint on this basically refrigerator door is off spec. You have to produce another one, etc., etc. So all of this basically data comes, live. So what we do is we do master data management, production planning and scheduling, inventory management, workforce management. We trace orders and also quality control purposes. And also we basically come up with the user experience, user interface, and the dashboard, right? Moreover, what we do is we basically create this representation, the other panel for management of the system, this is for machines. So individual allocation of more orders to individual machines. So it's a machine scale. So what happened is, system updates every 10 seconds. So we do replanning after a threshold is passed. And for this threshold is determined dynamically by machine learning algorithms. So whether a replanning is done or we can accommodate this change with the current setting, current speed. And the main result is production capacity utilization. So when we started this system, completely digitized, daily operation time to complete orders were 20 hours. If you are managing a factory, 20 hours is a very less than. The reason is you cannot have two shifts, because in Europe, 8 hours per shift. You have to use 2.5 shifts. So it's not 24 hours. So you will be paying 4 hours to your employees for doing nothing, right? So it's very basically bad. Either you are going to cancel your orders, etc. So we basically reduced this to 14 hours. And what happened is in 2024 March, sorry, my Spanish friends, but this company decided to close down the Spanish manufacturing facility. So Turkish facility has to absorb all of the production capacity. So we had this basically reduction of time and 2.5 million new appliances. Within 2 weeks, we did the training, in digital integration. Right now, basically, this factory is able to accommodate, 2.5 million new orders within 2 weeks. So it was basically an important, and also it basically considers machine-based capacity, etc., all of this. So the second is energy efficiency. This is again a global company, Chrysler's Turkey manufacturing facility, producing 450,000 cars per year. And basically, energy management is an important issue. You have process heat, you have basically air conditioning and cooling and heating of the facilities. It has a 2 million square meter of closed space. It's one of the largest production facilities in Turkey, right? So we basically, again, receive data from SCADA systems, PLCs, etc. And basically what we do is, in addition to basically managing the energy, we also brought them a microclimate forecasting system, because these humongous facilities have their own microclimate. So their basically temperature, etc., is a little bit different than the surroundings, because they are humongous and also they are releasing a lot of basically emissions. So with this, we were able to basically get this in operation. I'm going to basically talk to you about the results, and 1 minute I will finish. Okay? So in this case, we have a comparison between 2022, 2023, and 2024. So operationally, first 3 months of 3 years are compared, and our system became operational in January 2024. So electricity standard deviation is an important consideration, because when the electricity standard deviation is high, it means that you will not be able to buy certain quantity in the day-ahead market, but you have to purchase in intraday trading. And intraday trading cost of electricity happens to be 2 or 3 times higher than the day-ahead market. So first, you are saving a lot of energy. The second is waste heat ratio. So in 2022, it was approximately 27%. Energy was wasted. and 2023, 35%, and so far it is 3.86%, approximately 10 times increase in energy efficiency for this factor, right? So as a summary, it's a difficult problem, has to be solved very frequently, but I mean, we were able to see that reinforcement learning in combination with mixed integer linear programming models is helping us tremendously in addressing this problem. So we basically are encouraged to resolve this problem every 10 minutes. We are not basically resolving the planning problem every 10 seconds. It's basically down to 10 minutes now. With this, I want to thank you very much for your attention.